hollow. This is what we developed condition in working condition. Here also same. We have followed as per the design features. These are the features, and these are the what we did: armature, field coils, cable, and body. We did fabricate it also. Again, we used extensively FE tools to design and validate our designs. And what we achieved was this: we did fabricate all of the components. All of them are being realized correctly, and have been meeting our design criteria. And this has enhanced our instead of importing all critical, we are doing ourselves now. Right. So apart from the shakers, as I mentioned, you need some vibration testing elements like say fixtures. So what is the fixture is? Fixture is like intermediate component between the shaker and the unit to be tested. It has to faithfully transmit the energy from the shaker to the unit under tester. That is its main purpose. And its requirements, like ideal fixture requirements, like it is very less weight, very high stiffness. Means ideally it can be zero mass, but it is not possible, and very high stiffness. So that means optimum stiffness it should have, and there should be no resonances in the frequency band, and it should have good damping because it needs to be controlled, because we are controlling the vibration inputs. So what we do, we design number of fixtures for different components like this, which I have shown here, and we test it. We use extensive FE tools to design all these fixtures. We test it, and then accordingly we use. One of the important factor that required in a fixture design or say fixture fabrication is it needs to have very good damping. What is damping? Damping is a dissipating energy mechanism. For example, say if you have a good damping, number of cycles, it means if assuming it is underdamped viscous damp, what we mean is it comes to initial position very quickly. For example, you can see here, compared to this has come to initial position quickly. That means this is having more damping. Compared to this has come more quickly. It means this is having better than this. This one has come quickly, much better than these three. So this has more damping. Ideally, the materials that we can use are like say steel, aluminium, and magnesium. So of all the three, magnesium is having better damping. So we use for most of our fixture magnesium alloys. And if you see E by rho ratio, which determines the natural frequency as the frequency of structures that are being designed, E by rho for magnesium, aluminium, and steel are almost same. So that means if you design a fixture with either aluminium or magnesium or steel, your natural frequencies are going to be same. But damping is going to be better with this, so we prefer magnesium alloys for fixtures. Then how do you construct them? This fabrication, you can do a machining, you can do bolted fixture, different types you can use. But each type has its own disadvantages. For example, if you do a bolting fixture, means it can't have frequency range up to 2000. Machining is the best method. Then casting is also good because casting will introduce porosity, so that will improve the damping in the fixture. So either casting or machining is better. Welding will have its own problem. Likewise, there are some other methods which can be done. Now, having seen, say, we have been testing so many things. Suppose you have encountered a situation where you need to reduce the input, then how do you do? Let us see some of the methods that what we did. See, when we have a problem in the response, what we do is we follow this curve faithfully. What it means is, see, I have a source, I have a system. Source is my vibration input. The input is going to the system. From system, it goes to the in terms of response. Now, if I need to reduce the response, this response on this system, I need to attack either the source. First is try to attack the source. That means try to reduce the excitation. For me, it is not possible because I am giving a known input. As per my standard, I have to give a known input. But yes, source can be reduced in few cases. For example, if it is imbalance, yes, you reduce the imbalance. It means you balance the system properly. So your source itself, you have reduced the excitation. So their system is protected. So wherever possible, first you try to reduce the excitation as the input at the source. For me, it is not possible. So for me, what are the other things possible is like next you try to modify the transmission path. That means from the source to system, how it is being transmitted. It is transmitted through chassis or through structure or something like that. So if possibility is there, you try to modify it. So what we do is like this. We can introduce some kind of isolator here, I have shown you in the first slide, there was a case where we used isolator, but that has backfired. So we have to use isolators very judiciously. You can't use as always an option. You have to study the option of using it and then use it. So other option is you try to modify the system, means try to reduce the system frequencies or increase the frequencies, change the mass or stiffness matrix or the dynamic matrix, and then so you reduce the response. Most of the times this may not be possible to us also. So either we have to depend on modifying the source or this. We will see some cases where we modify the system, where we change the modified transmission path. This is not possible for us. And then there is a fourth option available, but we are not using or we can't use it in a way. That is, you try to read the response and send an opposite signal so that you get an active feedback system. Here, to have an active feedback system, you should have some generator also. Means generator means which can produce a signal. So you know the signal strength here and the phase. You produce exactly opposite signal onto the system. Now both signals will get nullified, so you will not feel the response on the system. Means the vibration levels you will not feel. This is done to some extent, what we call semi-active in some of the high-end buses, the multi-axle buses that nowadays we are getting. We are able to ride or say travel comfortably due to these systems. Active field work. It is semi-active, not fully, but they have been using in high-end buses this technique. That is why nowadays if you see our Garuda and other buses, vibration onto the passenger is this. Same thing. So when we are seeing that, we need to see, yes, I want to solve this problem now, suppose. Now what do I need to understand is the same thing. I need to know the source from where the vibration is coming. What are the frequency content and amplitude of that this thing? What is the path of transmission? What are my system dynamic properties? Once I know all of them, yes, I can tackle the system and try to change the this thing. As I same thing, I am mentioning different options available for reducing the vibrations. Like if you want to modify the source, yes, you do a proper balancing. If it is a fluid induced vibration, slashing by using corporate vacuums, smoothing of fluid flows, using multiple number of small nails instead of bigger ones. These are the different options available, like avoid vortex shedding of streamlining in the body or use helical spoilers to reduce the flow induced noise. Yes, we did one of the system modification. I just explained. We did quite few. One of them I will explain. In one of the Agni series of systems, INS, what we call as the industrial navigation system, which is mounted on some kind of bracket with the help of bracket onto the section. It means that where all the electronic components are mounted. This system was experiencing very high levels for the given input. The system was failing. So the problem was this: excessive vibration amplification and large differential causing performance degradation of INS. Differential input means at one end of this input, this system is mounted here using 4 lugs. So at one end of the system and other end of the system, you were getting differential. Even if both are same, okay, at least one problem could have solved. But they were getting here, amplification was different, amplification was here different. I have put here, you can see. The differential input is around like this, 22 GRMS for this input, 0.02, 0.03 if it was 47, 0.04, 58. This is very high actually. Whereas this system cannot take more than 3 GRMS. Here we are having 22. So then what we did, we studied the structure. We found that due to this structure pockets and other shape of the bracket, there is some problem. So we had come to conclusion that what we call as loss factors, as a damping in the system, can be improved if you know what is its theory behind. So when we saw, yes, it can be improved from beam type structure based on this formula. Then we found that cross section shape can be changed. How we changed it? We changed it, when we studied, we had this literature available. If it is I section, yes, the I section has more better damping compared to other sections. Right now it was like some kind of rectangle. So we changed it from I section to rectangle type, rectangle to I section, thereby enhancing damping. And then when we saw the results, these are the reasons why we choose idle section. It has more damping and more strength also. When we changed it, yes, this was the old beam, then we changed it the bottom and all that. What we achieved was, we achieved that amplification reduced and then differential input was reduced. The errors were less. When you see the final results, you can see these are being reduced by more than 50%, 2.5, less than 3. So all were less than 3, and then that is how the system worked. But to study these things, to know these things, we need to refer a lot of literature and how we are arrived on this. So like this, we can solve this problem. And there are few other cases, like say one of the IF4G, which fiber optic system. This is again an electronic package where at the initial design stage itself we found that response was very high. Means it was coming more than 16 times the input. It was not allowed like more than 2 to 3 times more than that input was not allowed. To check our design, we did even test also, just for other dummy unit, and we found the same kind of response was coming. So now we have to change the mounting scheme and other structure so that the amplification reduced from 16 times to it has come to 9 PRP. This so actually resulted in reduction of the amplification of around 1.7 times. So what we did was to modify the mounting locations. This is how we have reduced. And again there is one kind of electronic systems with what we call as a seeker, radio frequency seeker. Seeker is critical elements in the final target detection, final stage target detection. This was again failing due to the more input. Then we observed that we can change the boundary conditions of this structure so that the response can be reduced. So what we have changed was from cantilever to we have changed to fixed condition so that the response has come down. And there was one of our element in the vibration where we were not able to control the input, and there was like one peak coming. See, this crossing this red line which was not allowed. Crossing the red line means it is abort line which will fail or the system will trip. So to improve this, to reduce this peak, that means what we need is control, we have to bring it down. So for that we have enhanced it by improving damping. That is, we use some kind of thing called polyurethane foam. We fill it around this so that damping is introduced into the system. So the control has come from here to here. This is how we could use this system. So when we said these are the different methods one can attack. I mean, there are so many ways we can attack the system as per the previous slides. Apart from that, they were all modifying the system. Now let us see modifying the transmission path. Means what we mean is you provide some kind of vibration isolation. Where you are not able to modify the system, modify the source, you need to modify the transmission path. Isolator, as I said, this is some kind of resilient element. It is in between the input on the system. So what it does is it acts as a time. It takes the energy and releases it very slowly. So it time delay as a source of temporary storage and dissipates. Some kind of energy is dissipated in the form of heat. So one should be careful that the heat generated in the isolator is not causing damage to the isolator. And for this you should refer to the transmissibility curve. Why? Because what is the zone of isolation one should know. If you see the transmissibility curve of any system subjected to base excitation, you can see beyond root 210 the natural frequency, the transmissibility falls down. Transmissibility falls down below 1, means 1. That means this is the zone where you can isolate. This is how you should, for example, when you are selecting your isolator, you should know what is the frequency of the isolator and what is the disturbance of the frequency. So once you know the disturbance frequency, you should select the isolator such that isolator frequency is root 2 times the disturbance frequency, so that you are isolated from that. These are the different kind of isolators one can use. There can be like rubber isolators, metallic isolators, pneumatic isolators, like hydraulics, where all we use. These are all used for small subsystem level, package level, PCB level. These are used at a bigger level, container level, big mass, higher payloads and other things. These are again used at very low 1 or 2 hours kind of systems. These are used in some kind of motor automobile industry mainly. We don't use these things. But whatever may be the isolator, you should know that the reason of isolation is beyond root 2 times. That is the thing. So, by introducing isolator, what happens? There is a zone where you are amplifying the input. So that also you should take care, and you should be very well knowing that in this zone your system is not failing, but you are gaining advantages in this zone. Let us see some cases. Another considerations when you select isolator is you should be very careful with the weight, size, CG of the equipment to be isolated. You should know what are the types of dynamic disturbances to be isolated. You should know what is the static load of the supported weight, and also what is the static loading of the isolator also you should know. You should know the space allowed, means when you load a system and when you are vibrating, the isolator is going to have some space motion. That system should not have any obstructions in that zone, otherwise it is going to have a lot of heat there. And then these isolators are, suppose if they are made of rubber, then this environment plays a major role. You should know the rubber behavior at different temperatures. And then the service life is one of the other things is what is affecting the isolator. See, a poorly designed isolation system is better to not having proper frequency can be worse than the isolation, no isolation at all. Some cases where we have used isolator, example, another kind of system where we were getting very high input. So we need to reduce the input, means in the we have made some kind of isolation. This is before, see this has become 25 to it has become 2.8. But if you see the frequency, it is isolated frequency that has become very low. So you can see it is like a low pass filter. Beyond this frequency, it cuts off, beyond root 2, it cuts off every energy that is given into the system. So this is the advantage. But one should also be careful about this peak. Again, another kind of case, say when one of the RF seeker, we used isolator. Without isolator, with isolator, you can see the levels have come down. This is how the type of isolator we used is like this, kind of rubber isolators. It has 4 glass and some space. And while selecting isolators, we should, suppose you have a bunch of isolators, you should select from them what we call as a dynamically matched isolators. Dynamically matched means you have to test the isolator and they should have same natural frequency, and then you should use such kind of isolators rather than selecting arbitrarily. If you take arbitrarily, they may not effectively isolate. This is one kind of experience that we had is when we selected randomly, we did not get a better isolation. But when we are giving same input to the system, but you can see the blue is amplified, means randomly selected ones. When red is there, that is coming when we select matched isolators. Then suppose if you want to, any isolator is there to you, suppose, how do you test it? See, the manufacturer may give you some catalog of telling what to do, but you should have your own, just to say, you should have your own rated load, you put it on that, to excite it to the given specification given by the manufacturer and see what is the transmissibility. You have to see. In the transmissibility curve, you will get some frequency. That frequency should be same for all the systems that you are selecting to use. That's what we call a dynamically matched. Some locations for sure. Right. In one of the other systems where we have seen structural and other failures we have listed here, was this one of the flight recorder of LCA. So here also by using you can see that if the design is not proper, welding is not proper, you can see some failures due to vibration. So once say vibration is clear, then let us come to shock. Shock when we mean is a sudden transient impact of short time duration caused sudden change in either the acceleration, velocity, displacement, or it can be a force also. And what all does shock do is shock excites only natural frequencies and it can produce failures like this. It can have very high stresses that can cause fracture or permanent deformation. It can have high acceleration levels, cause relays to charter, bolts to loosen, high displacements, that means there can be collision between circuit boards, cracking, components, solar jacks, electrical malfunctions. Means they can occur during the shock but disappear when the shock is removed. So these are the failure modes, and then the shock can be very less time actually. Means it is defined like this. When a force is applied for short duration, less than the natural period of the system, then it is called shock. Right. In our system, where all we get shock due to these things, due to transportation, due to material handling, due to lift off noise. This turbulent boundary layer means that propulsion one is not in viscous manner, but in turbulent manner. Propellant combustion and stress operation. So what we do is we use some kind of shock testing machines. The characteristics of this shock is I have listed here. It can be amplitude, frequency, and duration of pulse. So it is relatively brief impact. A typical curve is shown here. See, it is a half-sine shock. What we mean is the acceleration. One is the acceleration, one is the time. And most of the shocks are, say, can be mechanical or pyro shocks. There are two types. What we call mechanical is up to 500 Hz because of low frequency we call. Pyro shock is due to pyro firing. It can be very high frequency and high amplitude shocks. So these can be generated in laboratory. These have some limitations. It either has to be generated by burning the actual pyros, means the actual detonators, or some kind of testing can be done. But this is what we do mostly. We convert these kind of shocks into this by some kind of studies, and then simulate these to study the structures. So what we use for simulating? If you want to simulate half-sine, you need to use some kind of elastomer pads. If you want to simulate, say, sawtooth, you need some lead pellets. If you want to simulate square pulse, you need some kind of pneumatic cylinders. If you want a trapezoidal, you need cylinders with rubber pads. Say, these are the typical things. How do we simulate this? If you want to say half-sine, if half-sine means like curve is like half-sine. You need, under this, you need to put this is a machine, suppose, between the impacting surface where the unit is going to impact, you need to have a rubber surface, or say we call elastomers. If it is a sawtooth, means if you want something kind of either say terminal sawtooth or initial peak sawtooth, you need to have some kind of lead pellets, lead syrup. If you want a square wave, if you want your wave like this, you need to have some cylinders underneath impacting surface so that to generate this kind of things. It can be brought by any other method also, means totally can be either by impacting force or some kind of shaker. These are different kind of testing, shock testing machines. It can be either pneumatic type, horizontal type, free fall, pendulum. These are different types. Pneumatic type, what we mean is we have a pneumatic cylinder in which one side, I know it's not. This is a pneumatic shock machine. What we mean is, see, this one kind of cylinder where you have one wall is open to one side. When we give pneumatic air, this gives to certain height, and then it is stopped using some kind of brakes. And then when you allow it to fall suddenly by impacting say another air here, this suddenly falls onto some kind of elastomers.